Good afternoon, everyone. I am Peter Anthony, a PhD student in my first year, and we are working on an improved classifier for learning and discriminating malware using knowledge-based embedding. And I'm working under the supervision of esteemed Martin Homola. Our major goal, we have two major goals in this research. The number one goal is to inject symbolic knowledge using knowledge-based embedding into a classifier in order to enable it to improve its performance in discriminating malware. And secondly, we want to achieve an approach that can be able to derive meaningful explanations for its predictions. For now, I will not be talking much on the explainability, as that will come in further presentations, but it's a core and a major part of the goal of our research. Now, quickly, as an overview, malware is a short form for malicious softwares, and it goes beyond just computer system to the servers and the internet and related fields. And there are different types and forms of malware. We have the Trojan, we have the worms, we have the bots, we have the adwares, we have the spywares, we have the ransomware. They are all different forms depending on the target, their purpose, and what it is meant to do. While when we come to malware detection, it's just the task of identifying and mitigating against these malicious or harmful softwares. And there are different approaches that have been proposed in malware detection and analysis. But broadly, we can classify all the approaches into three main classes. One is the static analysis or detection, second is the dynamic analysis, and the third is the hybrid. The static analysis has to do with extracting features from codes and malware structures and analyzing these features without having to execute the codes. Whereas in dynamic analysis, the analysis is done at runtime. In hybrid, it combines all these two with the hope of having an improved performance. Okay, this is what I just explained. Now coming to knowledge graph embedding, which is the core part of what we are discussing today. Knowledge graph embedding, okay, before I talk about the knowledge graph, the entire anatomy of a knowledge graph embedding is composed of 5 major things. One, and importantly, is the knowledge graph. With the knowledge graph, I'll talk about it. Second is a scoring function. The scoring function is a function that assigns scores to each triple. I'll talk about it here. To each triple in the knowledge graph. Then we have the loss function with M to minimize the loss. We have the optimization algorithm or the optimizer, and we have the approach for generating negatives. I also talk about or you call it synthetic negative. I'll talk about it. Now, first and importantly is the knowledge graph. This knowledge graph is the major input for a knowledge-based embedding. A knowledge graph is basically made up of collections of entities and relations and facts in a knowledge base, in the knowledge domain. Entities, collection of relation and fact in the knowledge domain. The fact is a triple. As we can see here, the fact is a triple made up of the entities and the relations. As we can see here, for instance, we have Liverpool. Liverpool Football Club is a football team. Now, Liverpool Football Club and football team are all entities, while is a binary relation that relates this and this. Now, in the fact, I say it's a triple. The triple we have in form of subject, predicate, and object, or some call it head, relations, and tell in any way you want to refer to is this represent fact. Now, the knowledge graph contains triples which represent true facts in a knowledge domain. It represents true facts in a knowledge domain. I talk about that in the anatomy of knowledge graph embedding. There are also what is called as synthetic negatives. These are manufactured facts that are not true. They are false facts. They are not true. So this is about knowledge graph. Now, the idea of knowledge graph embedding is to project these entities and relations that are in the knowledge graph or about the knowledge domain in a low-dimensional space. Depending on the geometric space it will be defined upon, is to project these entities and relations in a low-dimensional space. The idea is to learn the vector representations of these entities and relations about a knowledge base while the semantic meanings are preserved. This will also help in when trying to derive explainability of its performance. So it learns the vector representation of this entity and relation while the semantic meanings are preserved. Now, how does it really work? Now, any knowledge-based embedding model, how it works is this. Now, different entities and relations are in the knowledge graph. Now, these entities and relations are embedded in a geometric or low-dimensional space. Now, at first, what happens is this. The embeddings are initialized with random values. At first, they are initialized with a random values. Then, for each iteration, a particular size, or depending on the batch size that is specified, a particular size of the samples or triples are fetched from the training set, and they are used to update this embedding. As they update the embedding, it thereby maximizes the scoring function and minimize the loss. And this continues until a stopping point is reached. After that, at the end of everything, at the end of it, the learned embedding must have extracted the semantics of the entities and the relation in the knowledge domain and can be used now to predict a missing link. For instance, you are given, it can be questioned which country or which club does so player play for. You give it head entity, you give it the relation, and it can be able to predict for you the tail entity. So that is how this works. It's able to learn it and preserve the semantic meaning of these entities and relations in the knowledge domain. I've talked about the scoring function, which is a function that assigns scores to triples. Now, the higher the scores that is assigned to a triple, the more the chances that that triple represent a true fact. Now, when it comes to knowledge-based embedding, the scoring functions is one of the most important and the major difference between different knowledge-based embedding models. That is the scoring function. Now, I talk about generating negative. I'll explain what synthetic negatives are. Synthetic negative, the entire knowledge graph that you'll be using as your input are representation of true facts. All are true facts. Now you need negative fact called the synthetic negatives. How are these negative facts generated? They are simply generated by just corrupting the object and the subject. Now, the ways you do it is first way is you can just swap the object and the subject. That is one way of doing it. The other way of doing it is for you to hold the object and corrupt the subject by replacing it with another entity in the knowledge base, in the set of entities that does not represent a true fact. Another way is to hold the subject, corrupt the object by replacing it with another entity in the knowledge or in the set of entities that makes it not to represent a true fact. These are ways that synthetic negatives are being generated. For instance, now let's have a set of entities: Peter, yourself, book, Zachary, Takum, Arsenal, and we have set of relation, place for, born in. We have a true fact element of the knowledge graph, Peter, place for, Arsenal. Now, if we're generating synthetic negative, we have what? Here we just swap the object and the subject, Arsenal place for Peter instead of Peter place for Arsenal. Here we hold the subject and corrupt the object, Peter place for book instead of Peter place for Arsenal. Here we hold the object and corrupt the subject. It becomes yourself place for Arsenal. This is how generally synthetic negatives are being generated. Now, let's come to literature review. Several approaches have been proposed over time. Of recent, we have the RESCAL, which scoring function is based on low rank factorization with tensor products, introduced in 2011. We also have the Trans-E by Borders et al. In 2013. It's a translational based, it uses a translational based scoring function. The next 2014, we also have Dismooth by Yang et al. Uses a dot product. Also, Hall E uses, now those on black uses factorization based scoring function. Those on blue use translational based scoring function, and the green is of a deep learning stuff. Okay, I've mentioned that the major difference is the scoring function. Now, let's take, for instance, the Trans-E, translational embedding for multi-relational data. Now, the Trans-E is a knowledge graph embedding model that uses a scoring function that tries to force the entities and the relations to satisfy a simple, let's say, a simple vector sum equation. It tries to force them to satisfy a simple vector sum equation. If you equate this, it gives you the subject entity plus the relation gives you the entity. If you equate this to 0, it gives you the object entity. Now, what it does is it tries to minimize the distance between the embeddings of the subject and the embeddings of the object over the translation of the relation. It tries to minimize that. It's actually a very simple and efficient and less complex algorithm, but it also has its shortcomings. For instance, it does not model a symmetric relationship in a knowledge base. For like example of symmetric, let's say is married to a symmetric relationship for every x and y. If x is married to y, it also implies that y is married to x, but it does not recognize it. For it, we see example here. If Peter is married to Esther, it implies Esther is also married to Peter. This is a symmetric relationship. This is an asymmetric relationship. Peter is father of Esther. It does not imply that Esther is father of Peter. So the Trans-E only models a asymmetric relationship. It does not model a symmetric relationship. Let's look at a good illustration of Trans-E, and it also will give a clearer illustration of the entire knowledge graph embedding models. We see this at first. Now, at first, if you see, this is initialized with random value, and you see the way they are. After embedding this, the Trans-E is inspired by the translational invariance that is introduced in word-to-vec, and what it hold on to is that the fact that two entities will get close to each other. Two entities get close to each other after you have applied the right relation upon on the geometric space by which they are defined, so that it pulls them closer to each other. As we can see here, after the embedding, if you pick not 0 at the end of it, you translate it by the predicate, it should take you to this. This is satisfying a simple vector sum equation of the head entity plus the relation should give you the tail entity. Okay, I didn't talk much on this. This is just some relations types that are captured by different knowledge graph embedding. We see trans E that it models all except for symmetric relationship. We have models like Hol E, holographic embedding, that models all these types of relationship. Now, when it comes to evaluation metrics, generally in knowledge graph embeddings, it uses the mean reciprocal rank and the hit at K evaluation metrics. The MRR is just a measure of the proportion of the entire triples that are rightly predicted or ranked among the top predicted values to be correct, while the hit at K is a measure of the proportion of correctly predicted triples that appear in the top K position of the model's predicted rank. The evaluation metric is a ranking-based evaluation metric that is used in KGE. Okay, our progress so far. For our experiment, we are using the EMBER dataset, which is composed of 1.1 million samples, which includes 400 malicious samples and 400 benign samples, with 300 unlabeled samples for unsupervised learning. And we are leveraging the ontology that has been built in collaboration with colleagues at FAIR-STU, and that ontology covers the data that is enough for static malware analysis. So we are leveraging that ontology to build our knowledge graph. The EMBER dataset contains general information about the samples, header information, section information, import functions, and the export function, which are good enough for static analysis. Now, from the ontology, we are able to generate our knowledge graph with triples. For instance, we have these are individuals, the head, the relation, and the tail entities as generated in the knowledge graph, and they are converted into arrays which will be fed into the knowledge graph model. We also represent the labels as facts, also, which will be part of the data set. Now, in total, we used 1,000 samples from the EMBER dataset of 500 malicious samples and 500 benign samples. From there, we had 23 relations and a total of 9,614 entities, and the total triple generated or total facts is 63,358 in total. After running our experiment on 4 different knowledge graph embedding models, the trans-E, the holographic embedding, the complex embedding, and the dismode, we had our best performance through a holographic embedding with hit at 10 of 51%, while in terms of training time, the trans-E, which remains a very simple model, have the best performance when it comes to training time. Now, the evaluation metrics used in knowledge graph embedding, that is the MRR and the hit at K, will not allow us to compare our performance to other approaches for malware detection, because generally and commonly the metrics used in malware detections are accuracies, F1 score, precision, false positive rate, true positive rate, and for us to be able to compare our approach properly, we are working on a way to translate this performance back to these accuracies that are common, these metrics that are common with malware detection, and that is what we're already doing, and very soon we'll be done with that. Now, what is our future targets? First, what I have explained, we have two different types of link prediction in knowledge graph embedding. One is the transductive link prediction, the other is the inductive link prediction. In transductive link prediction, every entity and relation, when you are trying to predict a link, the entities and the relations must have appeared in the knowledge graph that it is trained upon. You can see this is the training knowledge graph, and there is a missing link you can predict. But in inductive link prediction, after training it on a knowledge graph, you can present another small knowledge graph, entirely different knowledge graph, and give it a different link, a missing link, and ask it to predict. A malware sample alone can form a knowledge graph with a label that is missing. Then it can be able to predict for you whether it is benign or malignant. Now, that is the next. Then, and most importantly, what we intend to go into and have the full of our goal is the more expressive approach known as the knowledge-based embedding. In knowledge graph embedding, in description logics, we say that it captures only what in description logic is called the A box, which is more of assertions about individuals. Assertions about individuals. Peter lives in Bratislava. Peter has height 20. They are all assertions about an individual instance. While knowledge-based embedding allow you to introduce constraints. Knowledge-based embedding allow you to inform what in description logic is known as the T-box informations. It allows you to introduce some kind of constraint. We can see, for instance, this class expression that is learned in standard. This is a class expression learned using parallel class expression learner. This method is what our colleagues in FAIR-STU is also working on, and it can generate some of these rules. Now, for instance, this is simply saying that a binary is malicious if it has multiple sections that are executable, and at least two of its sections has high entropy. Now, this is clearly defined. This can be used to enrich the knowledge-based embedding model. You have more of them, it enriches it and helps it to improve the performance in discriminating malware. And that is part of what we want to venture into soonest. Thank you, everyone. And your questions are welcome.